Yeah, recording has started. So, in this session, we will talk about feature engineering, which is which I have divided into two parts, part one and part two. Because this is a very important part in machine learning because when we get a data set, we get a lot of features. Now, what is the problem if we get a lot of features? Like for example, I will show you in this here itself. There are many data sets where we have a lot of features, and all the features may not be very important. And sometimes what happens is if you use a lot of features, that can result to model overfitting. There are two concepts in machine learning: underfitting and overfitting. What is underfitting and what is overfitting? Underfitting means that you draw a general assumption. Let's say you have let me take out paint. So let's say you have a thicker line, and I will use a red one. So let's say you have, oh, it is very this is fine. So let's say we have some data like this. We have this coordinate, and let's say we have a data point here, 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 right? So if what machine learning algorithm does is it tries to draw a line which represents this data. So this is your x value, this is your y value, and this machine learning algorithm, if you give it some x value for this, it will say the predicted value is y is this. If you say x is this, it will say the predicted value y is this, and so on, right? So, but what you see here is that the actual value is somewhere here. Like for example, if for x equal to 1, this y is equal to 3. But what this algorithm will do is, because this algorithm has learned this line, what this will do is for 1 it will predict something like 0.5, right? Whereas your answer is 3. So this is a case wherein your data and your the line so machine learning usually learns a function which is a line. May not be a line. If it is a linear function, it is a line, or it can be any curve essentially. So this is a curve which any machine learning model has learned. But you see, this line doesn't go through these points. Now in this case, what happens is that this is called an underfitting case, wherein you are generalizing it too much, because of which you are losing important information. Now if this line had gone through this could have, for this same one value, it could have returned 2.5, which is better than 0.5, right? So this is a case wherein your line or a curve that is learned by the machine learning model is far away from the points. In those cases we call it underfitting. The other case wherein, let's say you have again some data points here, some data points here, some data points here, some data points here, and some data points here, right? So, and let's say you have another data point here. Now if I learn a model which learns the exact curve like this, right? So if this is the model, the curve that you learn by the model, what will happen is for all this data, it will predict exactly the correct values. But what is the problem with this? So it is trained with these values, and that is why it is fitting. But if a new data comes here, it will not be able to predict the value, because if this curve is your learned thing, for this value your actual answer should be this one, which is, let's say, 10. But what the model will do is, for this it will predict as something like this, right? Which may not be correct. And also, let's say for you have a point here, something like this here, right? So for this it will say, it will tell some point like here, from here it will say, right? So which may not be correct. So in those situations, what we need to do is, we need a mix of underfitting and overfitting. So somewhere you have to find the balance, so the trade-off between underfitting and overfitting. We'll come to detail on what is underfitting and overfitting, but just remember that what overfitting does is, your model will do very good on training data, but on new data, while performing prediction, your model will do bad. That is called overfitting. What is underfitting? In underfitting, your model will do bad on training data and bad on prediction data also, but not on test data also. but it will be not as bad as overfitting. In overfitting on the test data, it will be much bad. So if we try to summarize this, let me say new again. If we try to summarize this, let's say we have two times train. Let's say this is train and we have test. Okay, test. So in case of so we have overfitting and underfitting, right? So in case of training time, overfitting is best. It will be very good. But on testing on new data, testing is similar as new data. This is very bad. On this thing, this is bad because on training data it is not learning properly all the information that is available on training data, and on test data it is also bad, but it is smaller bad. It is less bad than this bad, right? So you can say this is better. So if you ask in underfitting condition whether underfitted model will perform better in test or overfitted model will perform better on test, then the answer will be underfitting. But underfitting will do bad in both actually, but it is less bad in test than overfitting. Okay, so now what happens is, when you have a lot of features, coming back to this, when you have a lot of features, it results in overfitting of the model. So what happens is, although it will learn very minute patterns from the training data, but on the test data or on the when you actually deploy the model in real-time application, then you may get some data for which it is doing bad, right? So to avoid this situation, what happens is you should be very careful while selecting your features so that you can avoid underfitting. And there are other reasons also. One is that now the second reason is to avoid overfitting is one reason why you should do feature engineering. The second reason why you should do feature engineering is when you have less number of features, the training speed is faster. You can learn a model very quickly because it is dealing with less number of features. Model training performance improves. So these are the two primary reasons. But training is also okay because you will learn the model once. But what happens is, in real-time applications where your data is coming every week, so their training is also becomes important. Like for example, sales forecasting. So based on last week's data, you want to forecast your sales for the next week. So in those kind of situations, it is better if your training performance is not that long, because you can shut down your server for, let's say, 2 hours or 3 hours, but you cannot shut down your server for one day, right? So there also little bit of performance to improve training performance, feature engineering could be required. Okay. Now we will see the first way of feature engineering. There are different ways, and I have told you in this I have explained for which type of data set which feature engineering technique should be applied. Right now, first is the mutual information based filter method. So this is called filter method. Inside filter method there are different things: correlation based filtering, mutual information based filtering, and so on. We'll start with mutual information based filtering. But this is the most important one. Correlation based filterings are very linear. That's why I have not covered it in this notebook. Correlationship based filtering are linear based filtering, but I have explained in part 2 towards the end. I will show you that also in the second part. But compared to correlationship based filtering, mutual information based filter method is much more suitable. I will tell you why. It is because correlationship based filtering work on linear relationship. Now, what are these? What are all these we are talking about? So let's say you have 5 features starting from f1 dot f2. Maybe I will note it down. I will create a cell and say maybe there are 5 features or 4 features, let's say, and there is one target variable t1. Okay. So target variable are the variable that we are trying to predict. Like for example, in case of a Boston, let's say house price prediction. This is like city name. This is the location, area name. This is the square feet price. This is the number of rooms and so on. These are the 4 features, let's say. And target is T1 is the price of the house, right? And this is what we want to predict based on these 4 features. Now, what happens is, sometimes before actually learning a model, what we do is we want to find the relationship between F1 to T1, F2 to T1, F3 to T1, and F4 to T1. So this essentially can be done in many ways. So one of the ways is correlation. Now what correlation says is, if F1 increases, does T1 increase or not? If F1 increases, does T1 decrease or not? So there are two kinds of correlationship. It is called, these are like positive correlation and negative correlation. Positive correlation means if we are having, let's say there are two variables A and B, and let's say there is a positive correlation between them, it means when A increases, B also increases.
Yes.
So this is called positive correlation. But I will tell you what is the problem. Now in negative correlation, A increases, B decreases. So this is called negative correlation, and the correlationship value is always ranges between -1 to +1. Okay. Now if the correlationship between A and B is -1, it is most negative, and +1 is most positive. So what it means is, when the correlationship between A and B is -1, then they are negatively correlated and by maximum magnitude. So what it means is that they are very correlated but in a negative way. So if A increases, B will certainly increase, definitely. If A increases, B will definitely decrease. Similarly, if they are +1, then it means that if A increases, B will definitely increase with the best magnitude. So they are very highly correlated. Now when we are, and what happens if it is 0? When it is 0, it means that these two variables have no correlation. 0 means no correlation. Now what happens is, when we are talking about 0 correlation, so if in this case, let's say we are doing 4 features, and for this we found 0.8, for this we found minus 0.7, minus 0.7, and for this we found 0.2, and for this, let's say, we found 0. Now from this we see that this is positively correlated, this is positively correlated, this is uncorrelated, and this is negatively correlated. Now from this, if you have to select feature using correlationship matrix, then what it will do is, this is the best one, this feature is definitely required. This is also good because it is 0.7. This is okay, and this is bad. So if you want to remove any feature, this should be the first candidate that you should remove based on correlationship. And this is and if you want to remove 2 features, then these 2 features you should remove. These 2 you need to retain. Right? Now, why a positive correlate? What is the, now if this is helping, then why should I learn about mutual information and all? Why can't I use correlationship all the time and check, and based on that select my features? Now the problem with correlationship matrix is that correlationship value is that they are always linear. They only work on linear principles. Like for example, if X increases and if B accordingly, if A increases and accordingly B increases or decreases linearly, then only correlationship helps. But if they are increasing in a polynomial way, let's say A and A is related to B by A square. Let's say when A is 1, B is 1, A is 2, B is 4, A is 3, B is 9, and so on. Right? If it is like a square relationship or a polynomial relationship, in those kind of situation, this correlationship value will not be very good. I mean, this will not generate accurate values. So, and in most of the situations we see when we see in the examples, they will never be linearly correlated. Very rarely they will be linearly correlated. So example where the algorithm linear regression works fine, in those kind of problems, this linear relationship or correlationship will help. But initially, to do a first cut filtering, correlationship is fine. But feature selection, correlation, there are better techniques than correlationship. One such better technique is mutual information based filter method. Now what it does is, it is similar to correlationship. It measures, in fact everything that we will cover measures a relationship between one feature to the target variable, right? So all these things that we will cover will do the same thing. Now mutual information, what it does is, it not only captures linear relationship, but it also captures non-linear relationship like polynomials and all, square root, polynomials, other thing, all these things it will capture if there are in relationship. Now what mutual information means is that the term mutual means two, right? So mutual is like among. So if A and B is there, so among A and B, how much information does A carry about B or B carry about A? That is called mutual information. Now this again is a value between 0 and 1. So if 0 being lowest and 1 being highest, so if if the mutual information is 1, then let's say in this case it is 0, 0.5, someone is at my door. Just let me come back in 1 minute. Yes, sir. So, I was talking about mutual information. Let's say among these four features, this is 0. Are you there?
Yes.
Cool. So, let's say among the four features, it is 0, 0.5, 0.7, and 0.2. So, among this, the best parameter is this one. The next is this one. This we can say good. This you can say okay, and this we can say bad. So what 0 means is that this feature has no information about this thing. So if we look at this feature and try to infer something or learn a model, then this will not contribute anything much, right? So that's why it is called. I mean, this is a host one. I mean, these are all hypothetical. This may not be, because here in the correlationship I said it is 0.8 and this is 0. So these are just numbers. I mean, actually when you run the code, you'll see this is 0.8 and this will be also very good number, because correlationship and mutual information most of the times are aligned. I mean, should have similar values. In some cases where there are no linear relationship between features and the target variable, in those kind of situations, mutual information and this thing will vary. Got this point?
Mm-hmm.
Yeah. So we'll start with mutual information. So what I have done is, there is a inside scikit-learn package, there is a datasets module where there are some preloaded datasets. I have taken one such dataset, breast cancer dataset. Now this contains a binary classification kind of a task, wherein we say at the end we predict whether there is a cancer or no, whether there is a cancer or no cancer, right? With features of different types, like and the features are having both continuous and discrete values. Now, because of this, mutual information is suitable when there is a mixed type of features. Like for example, in these features, if some of them are numerical, some of them are categorical, and so on. If all of them are numerical, there are other approaches which we will see. But if it is like a mixed, then we should always, and the output. So there are two conditions. If your output variable is a binary classification, and your features are a mix of uh, numerical as well as categorical value, then you should use mutual information based filtering. Now again, another problem with correlationship is that if your data set has string kind of values, correlationship only works on number, it cannot work on strings, right? So if your data set has these kind of values also, you cannot apply correlationship based approach. So that is where mutual information also helps, and that is why it is said that if you have a binary classification problem and your data features have both numerical as well as categorical data, then you should always go for a mutual information based filter for selecting your features. Now let us start by analyzing this data set. Okay, let us see what it has. Okay, so what it is saying is, what I have printed first is that there is a x and y. What is x? X is your features and y is your target, right? Now what it is saying is, x has a 569 rows and 30 features, right? There are 30 features, and when I say y shape, y is 569. Essentially y has all the values 1 0 1 0 and so on. I can print, like it is a binary classification, right? So it has 1 0 1 0 1 0, right? So it is a binary classification problem. Now what we are saying is, when you create data or features name, it says there are so many features, like 30 features. Now, what was our initial problem? If we have so many features, it can lead to overfitting and all, right? So we don't want this many features, and that's why we are doing feature engineering. But we need to select some few features. How do you know which features to select? For that, you can use correlationship or mutual information, which will give you some value for each of these feature, and based on that, you can select which one is good, right? So for this, in this we saw that there are some data sets, 30 features, and binary classification problems, and out of these 30 features, we want to find which are the 4 or 5 best features which I should use. Now this number, you'll see how do I know how many features I should select, right? So what you can do is you can look at all the scores, all the mutual information scores, and wherever you find that there is a sudden drop, let's say out of these 30 features, 10 features have values between 0.7 and 0.8, and the remaining 20 are below 0.2. So you know there is a big drop between 0.7 and 0.2. You take all the features that are above 0.7, right? So maybe 10 features you can select, or maybe, and after testing, so machine learning is always a recursive process. You try with 10, and still if you think the model is overfitting, you come back and reduce again number of features, and then you retry. So this is, machine learning is always a trial and error thing, right? So you have to keep on trying and improving your model. So you start with some features. Let's say you start with 30 features. You see that your model is overfitting. Then what you do, you come back and do feature engineering. So to do feature engineering, uh, you select some, let's say based on what I said, right? You take a threshold. If the value is above 0.7, I will take, and let's say above 0.7 you have 10 values. You took all those 10 features, run the machine learning model again with those 10 features. You again test whether it is overfitting or not. If it is still overfitting, you come back again and reduce it to further, increase your threshold to 0.8, and let's say above 0.8 you have only 4 or 5 features. Take those 4 and 5 features and again try. So you have to, I mean, this is the process that we generally follow. Now let us see what we are doing next. We are from scikit-learn. There is a package called feature selection. Inside this feature selection package, you have all the different approaches. You will see inside. Next also, will most of the things will come from feature selection. Now what we are doing is we are getting the mutual information scores. How we are doing it? We are this mutual info class we are taking. We are passing our x and y values, right? And based on that, it is creating those index, and it is sorting those index by this, and this sorted index it is printing along with the score. So by highest to lowest, right? So it says that this all the feature, it is saying what is the MI score. It is 0.47, 0.46, 0.4, so on, right? So maybe what you can do is till this, let's say till this are above at least 0.1. Below this are 0.09 and so on. Like at least for this one, you can see it is 0. It has no information. This you can straight away discard. And at least this one also 0.07, 0.05. These all are very small values. Till 0.09, I think. In fact, 0.1 also. I mean, at least till this can be safely discarded because these are not adding much information for the model, right? So, but let's say you want to do usually it's good to have some number in mind, right? Like for example, I have taken k equal to 5. So if I take k equal to, so here what we have to do is, now this is the way in which you can see what are the scores. Now once you have the scores, what you do is there is a method called select best, k best. So what you do is you pass this score function, which is your which is the mutual classic function which is coming from here, and you say what is the k value, and based on that it will get a selector. Now this selector has a function called fit transform, which you pass x and y, and it will accordingly transform your data to based on these features. So it will remove other features and it will consider only the top 5 features based on this function, right? Now if I run this, what happens, you see it is like 569 comma 5. Now what was the initial one? It was 569 comma 30.
30.
Right? So now it has 5 features only, which is the top 5. Essentially, if you do further processing on this, it would have picked up these things only. I mean these 5, which are above 0.4. Right?
Okay.
So this is the first method in which you can select your features. Why I have done it in this way is that ultimately the goal is you have to change this data set, right? This data set is a 569 cross 30. Before sending it to any machine learning model, you have to convert it into 569 comma 5. one way you could have manually done it, right? So you, from this you saw that okay, these are the, or maybe from here you could have picked the names, right? Which one are the top 5, right? You pick those names and you apply and find the index of those in this, in this feature list. You find the index of those, you select all those index and create a new set of 569 comma 5. But all those things this function is doing it for you. So this, when you do a field transform, it automatically, and pass this function, this automatically selects the top 5 by passing this. But what, why I showed this is to show you, because I could have directly done this, but you need to see that what are the scores, so that you can understand, okay, based on this it is finding the top 5 and it is selecting based on this, right? So is this clear till this mutual information based filtering method?
There is one function about Ago sorts.
Which one?
Just a little bit about.
Here, tell me. Arc sort you're saying? This one?
Yes.
So what happens is, this ML scores essentially is a list of scores. If I just print it, no, sorry, in my scores. So this is a list of scores, right? But what we want to do is, we want to sort their indexes. We don't want to sort this. So if you see the sorted indices, so this will be list of index. So if we want to sort this, but so essentially we want to sort this, but we want to get the indexes after sorting. So this is a one line code which does this thing. It will sort, and this -1 means, so I have to tell you something, I think this you may not know. So I think 1 2 3 4 5. So let's say this is a list, okay? Now if I
Hmm.
do, so
Okay.
in this list if I say 1 colon 3, this is called list slicing, okay? So I made some bracket error, okay? Okay. So what it is saying is, it will find from the element number 1, which is 2. This I had actually shown you also previously. So from
Yes.
list number, this one, from 2 till 3 minus 1, which is this one, point number 2. So it is printed 2 and 3, right? Now what happens is, to this, I mean, I can say till 5, 0 1 2 3 4, 0 1 2 3 4 5. I have 5 elements, 0 1 2 3 4. We have till 4. So I can give till 5. And let's say I say there is a third argument which is called step. So
Yes.
start, end, and step, right? So
Hmm.
this is the syntax. Now if I pass 2, what it will do is, it will jump. So it will take, it will start from 1, which is 2, but it will skip this one and go to 4, right? That is what it is printing. Now it will skip this one and
Yes.
then it is ending. So based on that it is printing 2 and 4. Now what happens if I remove these two? So what, so if I remove these two index, it means begin from beginning, which is 1, a 0, and if I don't have anything, it will go till end with a step of 2. Now if we see this, what it will happen is, it will say 1, it printed this, it skipped this one, and it printed 5, right? Is this clear?
Okay.
Now if I
Got
want,
it.
now if I want to reverse this, what I will do is, I'll say -1. So if the step is -1, it will start from backwards. So it will start from 5 4
Hmm.
3 2 1, right? So if you see this, it is printing 5 4 3 2 1. Now if I do -2, what it means is, it will, minus means backward. So from backward it will start with 5, with 3 and 1, 5 3 1, right? 5 3 1, right? It started here, but it is -2, it is going backwards with a step of 2, 5 3 1.
Hmm.
Understood? Now
Yes.
what this arc sort, right? So arc sort is actually applicable on, let us do a type of this. Let us see what is the type. It is a numpy nd array. So this arc sort function cannot be applied on this list. Let me see if I can, if let me see if I apply it directly. Same code I will copy from here, and I will say a dot arc sort this thing, right? So it will say fail. List object has no attribute for arc sort. Now what I need to do? I'll import numpy. np dot array, and I will do this arc sort. np is not defined, so as np. What you are seeing here, 43210. So this is actually not the number. These are the indexes of those. You got it? It is not 54321. It is not doing reverse string. It is first doing reverse. It is first sorting it, and I mean it is reverse sorting it and then printing it as an index. So what it is doing is, so this arc sort is doing two things. First, given this list, it is printing, I mean it is sorting it in a reverse order. 5, 4, 3, 2, 1, and then it is finding out what was the index of 5, 4, 3, 2, 1. So essentially 4, 3, 2, 1 and 0, because 5's index is 4, 4's index is 3, and 1's index is 0. Right? So this is what arc sort does. Now if we print this sorted index, you'll see the indexes of the sorted elements, right? So it is saying index number 22 has the highest score. So which is host perimeter would be index number 22. So if we look at this, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, or maybe directly on this we can run a code. Why do I count? So it is saying index number 22, right? So is there a 0? Yes. So let us see what is index number 22. Sorry, what happened? Okay, bracket. Host perimeter, right? So it is saying host index number 22 has the highest score. What did we see here? Host perimeter index number is the highest score. Here we are doing this thing. Now this is a feature name. We need the index where the highest score appears. That's why it is doing a arc sort, because later on it is doing data.feature name and passing that index to get the name of the feature, right? So that is why it is doing arc sort on indexes.
So this is index is defined IDX.
This one you're saying it is from the sorted index.
Oh yeah,
Running a for
sorry.
loop.
Got it.
Got it, right? So that is why it is doing a arc sort here. Is this clear
Okay.
now?
Mm-hmm.
So once you have arc sort, you got the indexes. You are printing all these things. Now this is just for showing that how you can get the top k features manually. Now what you could have done is, you know, host feature has, I mean top 5, from reading this you know this, so you can directly get those index numbers, which is like index number 22, 23, 27 and 5 from here, and directly apply to X. But you have to manually do those things. But rather than doing it manually, there is a function select k best directly inside scikit-learn, which is inside feature selection. Select k best, and you pass what function you want to use to select k best, which you can say based on mutual information select top. Here you can pass other scoring functions also, like correlation and correlationship and all. So now you see how it has reduced from 569, 30 to 569, 5. Right? So this is the feed transform function. So first you have to create a selector object based on this. Once you have the selector object, on the selector object you call feed transform function and pass your x and y. Now this will return a filtered x based on this thing, based on this thing. And anyways y you have with you, y is already there with you. So this x is the problem. X is the feature set, y is the target. Now x is of having 35 features. We want to reduce it to 5, which we have done using this technique. Till this is clear, right?
Yes.
Cool. So the next method is wrapper method. Now we will use a diverged data set here for predicting continuous target variable. So here we saw it is for a binary classification problem, right? Use a 0, 1, 0, 1, 0, 1, right? Whereas for a
Yes.
diabetes, it is saying there is a continuous variable, target variable. So in this kind of situation where the continuous variable means it's a regression problem, right? So if the output is a output variable can be if it is a continuous value, it is not a binary value 0 1 or 0 1, then you can use a method called as RFE, which is recursive feature estimation or something like that. Recursive feature something selection. RFE, what is the full form? Let me check. I forgot. RFE full form. I think recursive feature estimation. Sorry, no, RFE full form of feature engineering. Recursive feature elimination. Sorry, sir. So here what we are doing is we have 30 features, but you gradually start eliminating some features. So where you have output as a continuous variables, you can consider using a wrapper based method. One such wrapper based method is RFE, which is recursive feature elimination, and we will apply it in the diabetes dataset. Okay, so let us see what the diabetes dataset is again. So here you see we have 241 records and 10 features. So here 10, not that many features, but still if you need elimination of your features, then you can adapt this kind of approaches. Uh, Now we see there are 240, 442. These are the features, 10 features, and you see the data is continuous. I mean, there is not like 0 1. There are many values which are possible, right? 100, 100,
Yes.
what it is saying is, uh, if you start taking a treatment today, after 1 year, what is the likelihood of, I mean, how much diabetes score will you have? I mean, whether it is will increase. So diabetic patient usually have some scores, right? So this is the score. How much degree of diabetes will it increase, or how much, what will be the level of diabetes? So this is the score that is getting predicted. Now again, as I told you, from feature selection package we import RFE, which is recursive feature elimination, right?
So
What
RFA is only used when it is a continuous value.
Yes, yes. When the target is a continuous value, and on the input side, when you don't have a lot of features, like you have 15, 20 features, but not beyond that. Okay? These are the situations. But it can only it is only suitable when your target is continuous. It is not applicable for classification problems. Okay. Now that is why you see here we are using a linear regression algorithm. Okay. Now what happens is, for RFE, it always takes a model. You need to pass a model that you want to use. Like for example, here we are using linear regression. I know we haven't studied about it, but you assume that there is a machine learning algorithm. We'll understand what linear regression is later on. But there's a linear regression model that you need to create, because this RFE function takes a model and n features to select. How many features? Let's say 10 features are there, but you want to select 4 features. So as I told you, how you do is you pass all the 10 to machine learning first, and then gradually reduce. So here you say from 4 you say 10. I want 10. So it will give you 10. So out of 10, because there are 10, you initially pass everything to a machine learning model, let's say to linear regression, and you get some results. Then let's say your accuracy is around 0.7 or 0.8, but let's say your target is you should have 0.9 accuracy. So what you will do is you will reduce some features using this technique and see whether your accuracy is improving or not. So how you will do it is, you will start with 9, 8, 7, 6 and so on, and see if it is gradually increasing. Let's say at 10 features you had 0.7, but if you change it to 8 features, your number improved from 0.7 to 0.8. Again you did 6, then it will improve from 0.8 to 0.85. But next time when you do from 6 to, if you do 4 and it becomes from 0.85 again back to 0.8 or 0.7, then you know that 6 number of features is the best feature, right? Understood?
Okay.
So
Yes.
how it is, you start with 10. Let's say you have 0.7 accuracy there. Then you reduce to 9 features, you get accuracy of 0.8. You go to 7 features, you get 0.85. You go to 6 features,
So
you,
how do we understand the model is taking only these features?
that I will tell you which features it is taking. That will come next. I mean, see, model right now, which features, like you said, select 4 features, right? But I think your question is which 4 features, right?
Yes.
That is the question, right? So we will understand that. I mean, that will come here in this block.
Okay.
So so Now, because that will also give you, that will give the analyst a more feel of which features are important. It is not about algorithm doing it, but algorithm should also tell you which features it selected, right? So that you also understand
Yeah,
that which features are important. Because if you need to explain it to someone else, you can say, okay, the model is
absolutely.
predicting this way because these features it has identified as important, and based on this it is doing this, right? Explainability of the model. Now, you have for 6, now let's say for 4 features, it got reduced to 0.75 all of a sudden, right? So you
Mm.
understand from 6 and 4, the accuracy is reducing. Till this, it was increasing, so you were continuously reducing the number of features and all. So here you understand from 6 to 4, it is reducing. So what you do is we again try with 5, and we will see that for 5 it is 0.88, let's say, and then from this you understand 6 is the optimal one. So you keep your 6 as the fixed number of features. The feature that you want to
Okay.
best is 6. Right? So this is how usually feature engineering is done. I mean, based on elimination based strategy. So this is an elimination strategy. So in this kind of approach you can follow. But here you don't need elimination in this. Like for here you need to have a threshold based approach. You can choose some threshold. Let's say select all features above 0.24. So it will select from here to this, and it will run. And then if you see it is, you will increase the threshold gradually, and if at some threshold it is the uh, accuracy is dropping, you stop it there, and you go back to the last best value, similar to what you are doing here. So that is a threshold based. Here you control the number of features to select here. Okay. So if I run this, what will happen is you will see that from for 440 to 10, it got reduced to 442 comma 4, right? Same RFE dot feed transform function is there, same RFE dot x shape that I am printing here,
Huh.
right? Now what was selected? Now there is a selected feature mask. There is a RFE dot support, okay, which tells you this feature mask is essentially nothing but the indexes of the features that is selected, right? So
Mm.
this you will get it through RFE support. Now what I am doing is I am passing this index, because this index is selected based on this selected feature mask, right? So what it does is it provides the index comma selected. So essentially what it is saying is this RFE support will return you of a true or false thing. So I think I should do something like this. So I'll show you what is RFE.support. So RFE.support for all the 10 features that you pass. No, this has 10 features, right? This X has 10 features. So for all the 10
Mm.
features, it will return true or false, and true or false, like this, right? False, false,
Okay.
true, and so on. Now for this, what we are doing is we are enumerating. So if you pass enumerate to this kind of a thing, no, what it will return is enumerate. If I pass this, it will return an enumeration, but enumeration has to be iterated over. For I in enumeration dot this, if I do print I, see what it is saying is index number 0 is false, index number 1 is false, index number 2 is true. So what I have written, if selected. Now what it is returning is a tuple. Tuple is having two things, index and selected, right? So if I doing, so you look at this part, okay, which is same as this thing. For I in enumerate RFE dot support. For I, so this I is a tuple. So if I say I comma j, so it is like, it is actually a tuple. So if you do I comma j, it will return both the values. So what it is doing, 0. So essentially I is 0, j is false, I is
Mm.
false, and so on, right? So if you run this piece of code, you will get index and select for each of them, and we are saying if selected. So if this is true, so if the second one is true, return that index or add that feature name to this thing, right? That is when this
Okay.
feature select. Now in this, if you see, it will return BMI, S1, S2 and S3. So these are the features that it selected using RFE.support. Now RFE,
Okay.
okay, so this is how you get the names of the selected features from here.
Mm-hmm.
I am keeping this here for as comment.
So we will get to know the feature names by only using the RFE support or the features mask.
Yes, using RFE support only once the model has learned, no, once the model is has done this feed transform. Before feed transform, there will be no RFE support, right? Once this feed transform is done, after that, if you run feed dot RFE dot support, it will give you indexes of like something like true or false and so on, right? So for each
Oh,
index, each feature, whether it was selected or not. So what it means is feature number 0 was not selected, feature number 1 was not selected, feature number 2 was selected. Similarly, feature number 4 was selected, feature number 5 was selected. Now, if feature number 2
okay.
was selected, what was feature number 2? Feature number 2 is 0, 1, 2, which is BMI, right? Understood?
But this RFE support we use when the target variable is continuous.
Continuous.
But when it is discrete, what type to understand what is the feature name has been used, what do we use?
If your target, if your target is not continuous, you're saying, right? If it is discrete, right?
Yes.
If it is discrete, you will not use this method at all. So this method of RFE, which is like this method is only applicable when your target variable is continuous number like this.
Hmm.
When your target variable is binary like this, you will use this mutual information, not use this one RFE.
But in mutual information, we did not came to know what feature has been used, the name of the features.
We knew na, we knew here it is printing these are the features, no? So you select, if you select the top k 5, you know these are the 5
Yeah.
features you are using. From this you can get know which 5 features were used.
Okay.
So so because this is using this function, you will not directly get from this selector from or is there let me see if select kbase returns a feature. This there must be something. Let me see if scores it returns n features. Oh, these are attributes. So scores. Let me see. So what we have done is we have done a selector. Let us run selector dot scores. What was it? Scores underscore. So it is saying scores for each of them, right? So this is returning scores, p values of feature scores. This is not number of features that are using feature names input. So these are the input names of the feature. So it directly doesn't give you the feature names. You have to find them out. So like what you can do is here you got the are we getting indexes somewhere? Scores? No. So, see, here you got the scores, right? So here it is
Hmm.
similar to getting the MI scores, right? Then you do again same thing, na? You do these things, arc sort on this. You do a arc sort on this, it will give you all the indexes, and then again same index as this one, right? From selector also you can get this thing. This is same as this one, and what we are doing next, you do all these things. You copy this. You call this sorted index indices. Sorry, what it is saying? Where data dot feature name index. Why? Oh, this data is different now. So mine currently this data is this one. So I have to reload this thing. So reload this data set. Run this one again. Run this one again. Now see, if I do this, it is giving you all the scores of all the features. Now if we are doing top k, no, what you need is you just say arc sort is -1, sorted index. If you want top k, you say colon k, so it will give you first k, whatever are the sorted ones. Sorry, what is the k? Okay, k is not defined. Oh, this is this k. Okay, so let's say top n, top n equal to 5. I define here. I pass this top n to this value. I pass this top n to this also. Okay. So here we get this. here we do this. See, these are the top 5 features.
Yeah.
Directly from the selector we got. So here we got it using directly using mutual info by passing this thing. Here we are getting it via selector. From selector we are getting the scores. That scores we are doing arc sort, and then we are iterating over it to get the top 5, top k.
Mm.
Based on, so it directly doesn't give you, I mean this API doesn't directly give you the features, top 5 features. So
Okay.
you have to write some code to get it up. Okay? So
Okay.
this is how you get top 5 features here. This is how you get top 5
4.
features, top 4 features here, right? Okay, so next is dimensionality reduction, but I think we are out of time. We'll close it here. We'll start with dimensionality reduction in the next session.